a lot for the invitation, and to say that we already at Greta at our seminar series on buffering, we already hosting Wolfram and Jonathan Goraz, so nice to see this is continuing. So I will speak today about something which I feel it's a development in theoretical computer science, which has been going on since about 2014, which was one of my main projects over the last 10 years. And it's about a relatively simple idea at first sight, but which might have some interesting consequences also for many of the algorithms you guys seem to be discussing. And so what I will tell you today is how a so-called compositional writing theory more or less automatically gives rise to certain algebraic structures, which could be of interest. And so of course, then the first question is, what is it itself, compositionality? So what does it? It is a technical term. There's philosophical versions of that term, but I'm going to talk about a certain mathematical sense. And to give you an idea how this arises, let's think of a prototypical example of a system where we manipulate graphs. So for the sake of the argument, for the moment, we're starting from an input graph, which may just be an undirected multigraph, if you wish. And then what I'm showing is a sequence of operations. So I mean, in order to not draw a sequence of graphs, I'm just showing it in one large picture. So this is going to be a sequence of operations applied, and I'm indicating where I'm touching something in the graph. So for example, when I create an edge, I'm telling you with the lines, where am I touching in the graph? Two vertices. There, then I add an edge. I mean, this is a little comic diagram. I maybe continue adding another edge. Maybe I delete some edge and create another, something very, very basic. Imagine this is an algorithm, a program you're running. And then after, of course, each operation, you get a slightly updated graph. And I guess this is a very, very prototypical situation in many fields of research. And now there's an interesting kind of question one can ask. So as this diagram already suggests, there is some very intricate relationship in principle, causally, between these are very simple rules, and yet there's already something quite non-trivial, you can say, once you go away from looking at stepwise, typically in a data set or in a data stream or in a program, you would have the individual states, so the individual graphs, and between each two graphs, there has happened something, a transition. And then you try to reason about these graphs, maybe put a metric, as Liubov was describing, or something like that, and trying to reason maybe how this changes in between steps. Well, of course, there's the other option. You can look at the way these transition operations themselves might have causally interacted in the sequence. And what I mean by that, imagine, for example, for a completely abstract sense, you were trying to figure out ways that this little rewriting system could create triangles. I mean, sure enough, there's a certain combinatorics involved because you're in a big graph. And I mean, sometimes you can by accident even create two triangles at once because they're adjacent already V shapes. You will immediately create two counts of triangle shape. And one of the interesting viewpoints compositionality offers, in the way I'm going to describe it, is that, well, let's look at the sequence. These are 5 transition steps, and I'm looking at whether at this particular market point, I create a triangle. Well, and I find out there were 2 of these 5 steps that created an edge and then deleted it again. So I mean, effectively did nothing in a certain way, even though it was not immediately one after the next, but in a way, one could imagine that we might wish to somehow discard this information that there was an edge, because in the end of the day, after these 5 steps, this edge has never been touched, it seems, right? So in a way, in trying to get to some sort of more abstract description how this writing system could produce triangles, I would maybe not wish to mention these 2 guys. And the other guys are really just stepwise creating between 3 points a triangle, which seems to be the canonical answer. How in 3 steps, you are guaranteed to get a triangle between these 3. This is all fine and good. But now somebody else comes and says, well, my graph is not a multigraph, so not one which allows multiple edges. Fine, nothing seems to change. I mean, this is a simple graph. I'm creating some edges, what should happen, right? The problem is now, this nice kind of argument I was sketching gets quite a bit more complex, because if you want to create an edge between 2 vertices, well, if there was already an edge, you somehow are not allowed to do this operation, right? So by creating an edge and then deleting it sometime later, You are no longer just doing another round, so to speak, but now the system has information that these two vertices were not connected in the initial state and are not connected in this particular example afterwards. And that is not no information. So the strange thing is somehow that by exploring a graph, by manipulating it sequentially, you are gradually learning something about its structure. So I mean, then of course, immediately the idea comes up, well, somehow could I learn with a rewriting system something about the statistical properties of a graph, for example? And as I was trying to sketch already this dependence on the precise type of graph you are doing, this is not an artifact. It turns out it is very important to know precisely your data structure because it will decide on which kinds of such arguments you might expect to hold.
And do you define the data structure as the initial X0 graph? What do you exactly mean by the data structure?
So first of all, I mean exactly what is our data structure, the graph. A graph itself is not a well-defined term. You have to tell me precisely which kind of graph, hypergraph, typed graph. So at the X0, for example, already there, you have to tell me what you exactly mean by graph. And then, of course, the next thing is what can be in the little boxes. I mean, what operations do you allow? And there's a very intimate relationship between these two design choices. And I will try to sketch that a bit, simply because to raise awareness that, yes, there's a certain cost to doing the kind of analysis I'm going to show. It has to do with being very exact about the data structures, which is in any event not a bad idea because you're going to program something at some point and you're forced to do it anyway. So I mean, it's not. But so the kind of the selling point of doing this in the end will be that what is already sketched here in this picture is that there is sort of a interesting property in its own right about these kind of this part of the diagram, which was how these different steps interacted. So a strange kind of wiring diagram kind of structure, which I call tracelets, because it'll turn out that such a shape of 5 steps interacting in some form will be a template for all possible rewriting operation in 5 steps with this particular causal structure on any graph you put. So that will be the feature of compositionality. In a way, the causality of rewriting steps interacting will generate the statistics, or depending on what kind of semantics you use, probability distribution even in a Markov chain of transitions. And what is interesting is that you might think that this has something to do with just binary relations maybe, and you would be right if it's about certain kinds. If you're talking about multigraphs and other very nice data structures, you can code with some sort of relations between inputs and outputs of operations. But the interesting bit is that already at 3 steps, how they can causally interact, something interesting happens that the output of the first guy drawn at the bottom here has a causal overlap with an edge that one of the endpoints is used intermittently. So if you draw it in one view, like all the steps at once, the causal interaction is actually of a half edge between the first and the third step, I guess, in this picture. Yeah. So in a way, this is already your hierarchy popping up right there, because this is not a binary, not a graph morphism anymore.
So just a question, I'm sorry, I will ask too many questions, but you put an edge here, between 2 edges, when you encode it.
Sorry, maybe I should draw this picture again. So I'm trying, imagine just each sorry, let me run this again. So on an input graph, I'm creating an edge between 2 vertices. I'm drawing on the bottom of a box what is the input motif here, just 2 vertices. And then I'm performing the operation itself, which in the top of the box is I add the edge, right? And I'm just having a shorthand notation to say, okay, I'm saying where I'm attacking the graph. But if I'm attacking with a second step, like for example here, create another edge, something from which was also the output of the previous step, I'm just using a different line color, just to make sure. Now I'm, for example, attacking this other vertex there. So the left vertex of the first step is also one of the inputs of the second steps, which can happen, right? They could completely run in parallel, these things, but here it so happens they interact in this way, right? And I'm only keeping, I could have drawn several steps. I mean, after X0 comes X1, which is X0 with 1 edge added, and then X2 is another edge added in this particular location. But you see, the tricky bit is that what really matters is this could be a huge graph and do everything completely in different places, then this would be boring. But here I'm in a situation where all the 5 steps had some sort of, they touched something which was used before, so to speak, right? Except for the first step, of course. Does it make sense?
And also the order, because you're familiar probably with the way how you read these diagrams.
From bottom to top, yeah.
From bottom to top.
Yeah.
Okay, thanks.
The end result is there's a triangle between the
well, not only, right? Because what I'm going to highlight to you is that even though your algorithm you'd write for the specific case would be analyzing how triangles occur, trying to explain how triangles occur, and so I'm counting the number of triangles in X0. That's a number. There's absolutely zero information of how the triangles were linked or anything. So how on earth can I go into this detailed picture where I'm rewriting stuff and expect that I get a formula for how the number of triangles changes on average in distribution or whichever?
But don't you do that just full all possible combinations, so it will be too much?
Exactly. So what I'm going to show is how compositionality in some cases can help generate formulas that effectively speak about the partial observation of the graph, namely by pattern counts, but still provide you with some information. For example, if this were a continuous time Markov chain and these steps would happen, basically the randomness is in where you apply the rules and whether you do the deletion or creation thing with some semantics.
Yeah.
So it is some particular kind of analysis, but it goes far beyond that because it also can speak about combinatorics of these writing systems. But maybe I should show that rather than just say it, because I'm sorry, we're stuck at slide 1. Right. So the big picture is that there's many techniques, and my motivation is from the life sciences. I want to understand bio and organochemical reaction systems, but I'm also open, of course, to looking at social network models. And there's many techniques that simply do not have any flavor of profiting from rewriting or transition-based picture, which is strange because many techniques in for example, Markov chain theory work a lot with knowing something about the nature of the transitions. So the main slogan is that graph-based systems are not Petri nets, are not just particle systems with no internal structure. And so the question is, how can you then extend these techniques from Markov chain theory to these transition-based pictures? And I mean, what I propose is that there's something called rule algebra, which is a certain kind of algebraic structure on interaction of rules, which has as a side effect tracelet theory, and I will exactly explain that next, that can translate some of these techniques to this rule-based picture. And then the question, of course, what do you do with it? And I'm going to try to motivate that. And we have nowadays, I mean, as I said, it's a very long-running project, so what we have nowadays is a sort of theoretical framework which is designed so that, in principle, at least for many use cases, you basically look at the bottom of this table. There's a way of deciding whether your particular data type and kind of transformations you're doing fits this compositionality paradigm, I'm saying, without understanding perhaps all the mathematical details which are on the top levels of how precisely we figured out what are the axioms that you need. So rather than, I mean, we could discuss mathematics, but I rather want to show you the kinds of diversity of examples one can already study right now. And of course, I'm very interested to hear if there's particular examples from hypergraph manipulation of some sort, then it would be nice to check whether this would fit the paradigm. So one very, very popular paradigm is what's called double push-out writing. I don't entirely know what's the background of the audience. Just to show briefly, there's an operation. A rule typically looks like some template, which has an input pattern and an output pattern. Think like in this little, I create an edge between the vertices. You are telling me what during the transformation you ask for an input, then you keep some part of it, let's call it K, and then you add some new stuff into it. So for example, previously I chose two vertices, keep them, and then in the final step add. So it's kind of an internal process where you first delete something from the input and then add something, lose something in for the output. And in order to do that, I have to exhibit what's called a match. So an occurrence of my input pattern in the graph. And then technically what I'm doing is what's called a push-out, complementary push-out. But rather than saying that, let me just show you, I mean, one of my motivating examples from chemistry. Here is a bona fide encoding of well, some kind of organic chemistry, let's say, maybe toy model for it. There's some graphical structures, and in organic chemistry, maybe you know that you never really delete atoms, you just rearrange electron bonds. So it's one of these typical examples. If you take a molecule on the right, that's the input template up top, then you try to apply that in a big molecule, and the transformation itself intermittently deletes some of the edges, but then recreates them elsewhere. And I think that's for the moment, that's good enough as an approximation what rewriting is. So you see already here, immediately, there's the point of what exactly is the data type. That is a difficult question. Let's skip that to the end. But just to say that I learned from some talk by Maxim Kontsevich that there's some mathematicians have some situations where they like to clone vertices in a graph because there's algorithms apparently where this is good for. So you might come up with something where you say, take a vertex, clone it into 2 copies, and then add an additional directed edge in it. Motivation being that connected things stay connected. And then here, for example, there's a non-deterministic choice to make. Basically, you clone the 2 vertices and you redistribute the edges originally incident to the one vertex in some consistent, in some way you like, meaning all could go to one or the other. And then, well, you add this extra edge in there. And here is the first hint at what is a kind of analysis that compositionality can give you. Because imagine you start out from a vertex, then you apply in all possible ways the rules. So first you just get an edge, but then already there is some ways getting edges pointing all the same direction or different directions and so on. I mean, very quickly you see, if you then, you typically in a program would not get this out of the box. You need to compare graphs by isomorphism. But if you do that, you already get a sort of combinatorial distribution that evolves. That in each generation, you can say something about the number of ways it was possible to reach a certain configuration. And I mean, this starts to look a lot like any other dynamical system you can imagine, only that its basic generator was just one rule. So that's already quite interesting. If you do this...
But it's still discrete.
For the moment. Yeah, for the moment.
It's not continued production.
No, for the moment, it's just a combinatorial analysis you could do. And I mean, already you can imagine that depending, if you have a problem and you compare instances of the problem and you think, oh, maybe it is related to some generation procedure. I can get one from the other through manipulations. It might be interesting to look at how these steps then can interact, right? So one would like to have some sort of causality analysis or other deeper picture than just looking at instances. And this is a kind of analysis that's possible. And I mean, just to say there's other variants. For example, there's a way of cloning where you basically deep copy everybody. So all the edges that go, funnily enough, you then generate the directed simplices and iterations. So in all the isomorphic ways. So
something like percolation, you have a big graph. Here and come there, and so at some point it's not synchronized.
Yeah, exactly. If you do the soap bubble thing, actually, exactly. So when you cut and anybody who was linked to you pops away. Yeah, exactly. Yeah. So that's another kind of semantics code. Technique is called Sesky push out in our language, but it has exactly this feature. Yeah, that you kill connectivity.
Something like Polish edges and.
In fact, you can
Average coordination number.
Yes, for example, if you do tessellation of the plane, there's these 3 von Neumann rules up to the parameterization that you can only perform to keep exactly this Euler characteristic, and that you can also simulate. I've actually worked on that too. So I mean, it's a very, very expressive framework, and I mean, most amazingly, if you look at biological cells, it is simply a fact of this research field that you have some idea of how entities like molecules and enzymes interact. Usually it's not a complete knowledge because simply, I mean, experimentally, it's not well known. And if you look at any research paper in biochemistry, there will be a pure text description which reads something like, I don't know, some wild name of enzyme. If it has that and that site and it is phosphorylated and whatnot, then something will happen. And what I found most impressive, what really drew me into this field was that Vincent Lanos and his co-workers who actually founded or co-founded, I guess, the Cree Institute also, in the early 2000s, they realized that by giving a data structure that can model precisely these kinds of sentences. So it is a data structure where basically you have so-called agents. So these would model macromolecules. About these agents, some partial information is known, that they have certain positions, like your papers, they have certain keywords. And then maybe these positions can even, in biology, they carry sometimes extra datum, whether they're phosphorylated or not, so they can be modified. And then the key feature of this is that there can be a rewriting operation on this, which does not ask all the information you could have on a molecule. I mean, imagine if you had enzymes which can have 10 different active centers, and on each you have activation or deactivation, and then to write down all the rules how you can get between these two enzymes to just simply link them, or you would have an exponential number of things in the number of sites on each. It is a huge advantage if instead you can just say, I partially observe this thing, and if there's enough information, like in this fraction, I can do a reaction, right? And also later, if I discover there are more sites, this wouldn't even interfere with this. So it turns out that it's so efficient as a language already that this is nowadays the standard of how biochemical databases, or one of the possible standards, how they are called. This is a real life data structure. And then, of course, same idea, to model a biochemical reaction system, you take exactly this coding. Now, of course, you need an efficient simulator. That was what much of the work went into the past 20 years. But then you can do trajectories of such a complex real-life biochemical system by doing local manipulations according to the rules you just gave. But the key point being that these rules only ask partial information. So you only have partial information in the rules themselves. Now, of course, it's interesting once you start plugging many of those together on a concrete sequence, to get a complete sequence of graph states, you can ask how did they interact. It'll turn out oftentimes that while for one reaction you only need partial information, once you want to plug them in a certain way, suddenly you need data overall on more of the sites of the enzyme to support a certain sequence of events. And of course, that is exactly the kind of output that you want for analyzing possible targets for drug development or something like that, right? And it's interesting that this Kappa project was quite a success in bioinformatics. There's even a website where you can, a web interface where you can run simulations from a web browser. There's no analysis of compositional properties. So that is still one of the really big challenges in our field. And I wanted to say, in this huge paper I said, I mean, even though it's theoretical, there's a table, as you can see on page 45, so I mean, it's a long paper, but where for the purpose of sort of giving a database of things you already know support our kinds of manipulations, you have a long list of data structures, including undirected graphs, directed graphs, simple graphs, hypergraphs of all sorts. And also there's a little, it's not yet very, I mean, there's a certain vocabulary of constructions from known cases you can do. If you have a very specific data type, a very particular kind of hypergraph you think needs special attention, because for a hypergraph you have to tell me the vertices of a hyperedge ordered. I mean, like a list, or are they more like a set? I mean, do you not care how they are ordered? Is a hyperedge directed? Can a hyperedge have endpoints and start points, and so on? I mean, and each case warrants a little bit of a different viewpoint, but we give you a list of constructions that, I guess, for hypergraphs, and on top the vertices can have kinds, the edges can have kinds. I mean, there's a list of constructions that hopefully give at least a starting inspiration that your data structure might support this. And I think it's important if you write programs to maybe check if it's in any of these, because I mean, it'll give you extra guarantees on okay. For example, if you want to do a continuous Markov chain based on transformations, which you might want to do, if you want to do a combinatorial argument, your data structure does actually not support this compositionality, then you're basically producing white noise. I mean, to be harsh. I mean, essentially the continuous Markov chain, you can only partially observe it, typically, because I mean, it's graphs. So then the statistics you get would not be representative of the process if it's not a compositional writing system. That's unfortunately the situation, which is why this might be important in your scenario. And so, yeah.
Here's the way incidence, single incident.
Well, it's just because if you have an undirected hypergraph, normally you would speak about the source and target. I mean, it's just a name for, I mean, hyperedge is incident, it touches those vertices. Yeah.
So what do you mean simple? What is that? What does simple?
Well, I mean, you might only be allowed to touch. I mean, like double edges. I mean, you might only allow if you choose two vertices. May at most be. I mean, like a hyperedge of a certain arity between them or not. You might allow bubbles or not. You see what I mean? Yeah.
And you say some constructions to categories with recursive properties. So these are two possible just examples.
Yeah, but they give different kinds of structures, and then that immediately influences what kind of rewriting operations you can perform and expect to have a good compositional property. So for example, if you pass from multigraph to simple graph, like in the example in the beginning, then it turns out that in order to have you remember there was this weird feature, if you create an edge and then delete it, for multigraphs this is a null round. We have not learned anything about the graph. Any two vertices support this sequence of operations. While for a simple graph, only two already disconnected vertices support the operation. So this seems like a conundrum. How would you carry the structure within this compositional picture? And it turns out it's possible because for the one case, you just choose embeddings with no qualifier for the input motives of operation. And for the other, you have to choose what's called regular monomorphisms, so edge reflecting. So if you embed two vertices that are not linked in your domain graph into a target graph, they cannot be linked in the target graph. And that, if you think about it, that exactly explains that once you apply this create and delete sequence, you already know, because there was an embedding of two vertices with a regular monomorphism in the graph, that at this point, these two vertices were not linked. So that information is persistent, which would not be the case if you have arbitrary monomorphisms, because you don't know anything about just embedding two vertices, right? Do you see what I mean? So basically, you go on the list, you see, okay, I have my, let's say, a simple hypergraph, then you already know, I have to be careful. If I want to reproduce this, at least I need to use regular monomorphisms, whatever that is for a hypergraph. I mean, there's also a notion like that. Morally speaking, similar idea. Yeah. So it is a decision grid, so to speak, which hopefully at some point we will elaborate a bit. So if you have any feedback on what is my time budget?
About 25 minutes.
Okay, good. So I'm going to show you briefly, and because I mean, again, this is a workshop on hypermatrix theory and hierarchy and so on. So I wanted to show you precisely what is the nature of hierarchy, if one can call it that plays a role here. And also to say this is a theory in mathematics, the composition space theory, which is a very well-established field by now. And one of my collaborators, Joachim Koch, is actually one of the people who really, really pushed this, especially for applications computer science. And it is quite interesting that this very general mathematical theory fits perfectly understanding what is this notion of compositionality we need in this particular kind of setting. And so, again, have a look at sequences of transformations. And I write here, this is double push-out writing, but I mean, imagine it is your chosen semantics. And what we want to understand is if you have a sequence, we go from x0 by applying a transformation to x1. Let's say locally we add an edge, and we do another operation, go from x1 to x2. So we look at stepwise modifications of graph. And now the point is, what we would like is that we can somehow extract from this how the two rules and quotation marks interacted. So did something from the input of the second rule touch on the output of the first? I mean, mathematically, what we are going to use is called a multisum, but that's not important. Let's imagine there's a way of extracting the smallest graphs that contains the input of the second and the output of the first, so that so together these two embeddings are surjective. So I mean, I'm only keeping everything that I need to find I2 and O1 in this intermediate state, right? So it's the smallest graph that has this property, let's say pre-shift opposites. And then I just take that as, basically I take this intermediate state and just again rewrite forward with rule 1 and against the stream with rule, forward with rule 2 and against the stream with rule 1. This is for reversible semantics of transformation. It might not be in every, if it's not reversible, if I can go against the flow of a transformation, then okay. But let's say here it is. And this gives me this weird looking diagram. So I now have basically the first two lines code for sort of the minimal event sequence that I could have had to see this particular overlap between the output of one and the input of the second. So it's like a minimal scenario where I could have seen this particular causal interaction. And then it so happens to be applied to state x0. And of course, I can forget that intermittently I had two steps and just do I go from x0 to x2 by simply basically composing out these two steps. And now this is exactly the data that you had in these diagrams in the skies. So it's exactly, the top bit is how these two box diagrams were wired together, and the bottom bit is how then they together transform from x0 to the output state. Okay, probably I'll share the slides, it probably takes a moment to go back. And then conversely, so exactly, sorry, where is it going again? Yeah, exactly, I want to get to this state, exactly. I have a structure which sort of a minimal sequence, how it's possible to interact in a certain way, and then I just apply that to the input state, directly get to the output state. And conversely, of course, it would be useless if I weren't able to always take this data and reconstruct a complete sequence of two steps, right? Mm-hmm. So that's basically the reverse direction, which also needs to be possible. So basically then forgetting intermittently how they overlap and just reproducing a two-step sequence that needs to be completely compatible. Otherwise, my kind of analysis is a little bit artificial, right? And then immediately, and that is something I found it quite funny because I'm originally a mathematical physicist, and this kind of piece was completely clear to everybody doing rewriting in this particular community. It's called the concurrency theorem for traditional reasons. And that is a structure that was well known in rewriting. Strangely for me as a physicist, and of course immediately you want to play with it, and I mean, you sort of think, okay, if it works for 2, what happens with 3, right? And it turns out here is a problem because mathematically the only thing that is well defined is a binary direct interaction of immediately consecutive steps, like the way we did before. But then you can ask, okay, but now I have this top bit, which is a minimal sequence of the first two guys. That of course has some sort of interaction with the third rule, and then I can extract it. Why not? And now all I'm doing is I'm going to, and it turns out, if I can do that also in the other order, first looking at how 3 with 2 acted, and then with the first, I've extracted the minimal derivation sequence now of length 3, and it'll be one of these wiring diagrams with 3 boxes where this new effect can happen, that maybe a half edge of the first guy is mapped into a half edge of the last guy. Right, effectively. If you look at
here, it's simultaneous or not,
well, the steps are consecutive, but I mean, then there will be a possibility to look at things that could have been applied in any other order. But for the moment, they are just consecutive. But the way they interact, when you look at it, you cannot directly look at how 3 interacted with 1 in this picture.
Yeah, exactly. Like here you can.
And now this is an intrinsic feature, it turns out, not just an artifact. So it'll be this decomposition space theory, actually. But for the moment, let's just say we could go on. I mean, as I said, like you should be able to extract this 3-step minimal sequence in either order of nesting of pairwise consecutive compositions. And then extract from it what I call tracelet length 3. So a template for 3-step transitions that has a certain causal order, which is possible, right? And of course, later we will only look at these interactions and not at potentially huge graphs where they could be applied. Okay, and so the trick is that you basically lift individual transitions to a degenerate case of tracelets of just length 1. You just apply the rule to its own input motive. I mean, do nothing effectively, but just have the rule there at Cité. But at length 2, you compute the possible partial overlaps of 2 rules, I mean, the output of one with the input of the next, and then complete out these pictures to get 2-step sequences. And at length 3, you choose either order of generation. I mean, either first 1 with 2 and then composite with 3 to get the tracelets and so on. So that defines inductively a data structure, right? And one could say it's compositional because there's nothing in this algorithm that makes anything special about 3. And it's actually easy to prove that you have 2 such minimal sequences. You can stitch them together by choosing an overlap of the overall output of the first with the overall input of the next, and just there's basically a lemma which tells you can effectively just rerun all the steps in this the second sequence to the left and the first sequence backwards, and then compose vertically, and that'll give you a composite thing, which so happens to again have this minimality property of classifying all the m plus n length sequences with that particular causal order. So there's one lightweight thing to say about, in this way, it's let's say, causally compositional. And it turns out there's a much deeper reason. This is a data structure that arises and has mathematical properties, and it has to do with precisely our intuition, what we mean when we look at these little wiring diagrams. So imagine now in these three boxes, I have three operations I want to perform. I somehow think that they are sequentially applied, and I want to ask they somehow interact. Now, it's easy to think one thing produced from the first goes into the second. That is not rocket science. And we sort of want to be able to black box and say, aha, and these two together have this and that effect, right? And what we want is, this is a sort of persistent structure that anywhere in a sequence of stuff I apply, I can box subsequence of the steps and look at their interior, and so, for example, completely black box them or partially black box them to causally analyze them. And for that to be consistent, what needs to happen is that if I, for example, take the blue black box around step 3 and 2 to produce a composite, I'll produce a wiring from the composite to the bottom guy, and that itself, when I then black box that thing, needs to reproduce the same net effect of the three-step sequence than if I had just simply applied the three-step sequence or black boxed another way. And so overall, so if one looks closely, there's 4 projections I can do on a minimal thread by these manipulations. I can produce in black boxes, and I can produce composites of 2 steps sliced into position with another non-black box step. And now there's a very, very powerful concept in mathematics called decomposition spaces. It turns out in this particular flavor, it'll immediately make a link to combinatorial Hopf algebras. So it's along the lines of these ideas of Feynman in particular. So if you look again at this picture and count the number of ways you can extract data from a three-step sequence by projecting out from any of these shaded regions up there, you find exactly 4 projections. You find the 2 consecutive black boxings, and then a black boxing of how these 2 guys were sliced in place. Basically, you can read out the shaded blue region, pink, yellow, or red, or orange, I guess. And this is not an accident. It turns out this is precisely the mathematical structure at play here. So concretely, sorry, I lost the slide. This is not good. Interesting. Sorry, let me just recover my, oh no. Huh. I'm very sorry, I somehow must have accidentally deleted the slide. Okay, anyways, let's go at this picture. So the 0 simplices in this structure, I mean, so this would be a simplicial groupoid. So basically at each degree, I have a groupoid. And then the objects at degree 0 are just dummy, it's a one dummy object. At degree, the 1 simplices contain, which are the lines here between, for example, simplex 0 and 1, contain the rules, so the structure that I use to rewrite. And the 2 simplices, the triangles, contain exactly the data of how 2 steps can causally interact to form a net effect composite step. So each of the triangles turns out exactly data of who composition is double preferred semantics. And now the key point is, what then is this weird property that I cannot reason directly on a 3-step sequence, but I have to go through this nesting. But I want it to be that if I compute some minimal representative of 3-step sequence by nesting 1 with 2 and the composite with 3, why should that be compatible with the other way around? Well, pictorially, diagrammatically, it's exactly that if you stick two simplices in this particular way, then one should be able to fill the entire 3 simplex, and in particular also the other 2 phases. That's the statement. And this is exactly done through the concurrency theorem. This, back and forth from composites, I can construct sequences and the reverse. So you can exactly go inside this tetrahedron, and by taking, well, certain pullbacks, pushouts, and so forth, you can do the entire tetrahedron with its interior. Turns out that two adjacent triangles, the two simplices, code for the sequence of 1 with 2 and composite with 3, or the other way around. And the inside is exactly the data needed to mediate between the two representatives. And on the inside, if you see, is exactly this data of a tracelet. So somehow tracelet is something truly non-binary in that sense. It's a true higher order interaction, and it has to do precisely with the statement that it is in interaction with the binary operations, because it codes for possible nesting sequences of binary composition. But it's a true, non-trivial higher order interaction. And if you want the fancy thing, so there is a statement that, for example, what I just showed, that two adjacent faces, I can universally up to isomorphism create the other two adjacent faces, is exactly the statement that this is a homotopy pullback. I mean, I don't know if Xerxes is here, but he might be happy about this. Anyways. Well, and then basically the upshot is that what I call compositionality is basically the guarantee that once you have verified the property at the three simplices, that then the higher order simplices are basically obtained by all possible gluings, and there's no internal extra data of a four simplex that cannot be recovered from C simplices. So that's what's called a decomposition space of a certain kind. Okay. But long story short, what the mathematicians do not usually do, now in our analysis, we typically, especially if you do Markov chains, we do not want to consider two steps different when they are just applied in parallel at different points. So I mean, even though there's of course a sequential order how we saw these steps, we don't really want to distinguish them. So we want to somehow have a notion, pictorially you want to be able to write diagrams next to each other rather than sort of keeping artificially some order, right? And on top of that, we usually are not interested, especially if you go into Markov chains over graph-like structures, you have to go to isomorphism classes, it turns out. So in particular, we are not interested in isomorphic representatives of a minimal sequence. And if you plug all of that together, the equivalence by sort of representatives on each graphical structure, the equivalence by what's called the shift equivalence. And on top, I mean, of course, there's one special trait, which is if you do nothing, really nothing. You ask nothing, you do nothing. And you have many copies of that. You probably just don't want to keep more than one copy, right? Or if you parallel execute do nothing, which is a null round in the simulator, with do something, then you just want to keep the do something. Putting all of that together and putting in equivalence relation, it turns out that this particular kind of structure precisely gives rise to combinatorial Hopf algebra. So ordinarily, you would just get an algebra, as I will show the last part of the talk. But this really bona fide gives rise to combinatorial Hopf algebra, and that was, for me, one of the motivations, because I started working with Gerard Shaw and Carol Penson on some problems in normal ordering, which happens to be a special case of these writing systems, which I'm happy to discuss offline. But okay. Anyways, so final bit. So what now is promised effect of having compositionality? What practically do we want to do with it? And here is something which, I mean, I could tell you exactly how to get it from the decomposition space theory, so that it's now really no longer a hand construction. But I'm going to show you just the algorithmic way to do it, because simply for the first intuition, it's better, I think. So if you give me any such template for rewriting stuff, input, output pair, and somehow what you keep, first step is I will now construct an auxiliary vector space. My vector space will be unusually indexed not by some abstract set or something, but isomorphism classes of such objects. And here I mean, however you write your input and output graph and how they are connected, it only matters up to relabeling in all of these applications. So let's call that a basis state for a class of such things, delta of R or delta of such rule. And then there's this operation that we saw already pictorially, where now each of these little transformations knows how it can be wired together with others. I mean, You pick a partial overlap morally, and then you evaluate essentially what's the net effect. Once you have partially overlapped, you get a composite rule, right? So you can use that operation to define a binary. So you have a vector space with now a certain binary operation on it, which I call rule algebra product. And it does on basis vectors, again, indexed by subclasses, exactly the sum of all ways to wire together and then evaluating. Now that produces non-negative integer coefficients often, because there might be two different wirings that can produce the same composite rule. I mean, but that's how it is. Again, the operation, you select your semantics for rewriting, you tell me what is this particular overlap structure. But I mean, we can do that for many cases. And this is a picture to have in mind. But that's already interesting. So nowadays we say because of the decomposition space theory, there's a certain, so decomposition spaces are groupoids. So there's an operation of degroupoidification, which is precisely just taking representatives. And then the binary operation I'm showing here is precisely a convolution product of a certain sense on that decomposition space. But in particular, so I mean, what I'm saying is will not be surprising for mathematicians of this field, but this will give a unital associative algebra already. This is maybe non-trivial, but I mean associative precisely because of this weird tetrahedron type of interaction guarantee. And that was basically something not known in the field. So it's the starting point of any of the other theories you can do with rewriting, I guess, or you want anything like a Markov chain, combinatorics, and so on. And now the second bit is we wanted to do rewriting. This is only just abstract interaction. So how do we get we want to use this now to actually rewrite, of course, right? And here the inspiration came from chemistry. So if you have a chemical reaction system of the very simplest kind, it is a rewriting system on just multisets. Let's say even of just sets here, because I mean, only one kind of atom. And it asks, operations are take out an element and add in new elements. And the semantics is that the taking out is combinatorial process of picking from an urn undistinguishable particles, right? So picking one particle is possible in n ways if n is a number of particles. So, and the ingenious work of Max Delbrück was to then code that in formal power series calculus. So that was in the 1940s. Basically, rather than giving a very elaborate explanation of how the semantics works in words, we just give a mathematical formula. So we map a state of being in n particles as a monomial x to the n, where x is a formal variable. And we write the operation of how in one step the state should change infinitesimal. Infinitesimal, you have one or no jump. And the only one jump you can do is here, take out one particle, make two. And so for a Markov chain, it needs to be the case that the probability mass that you move somewhere else in the distribution needs to be, of course, deduced from the current place so that the net flux is zero probability mass. Well, here's an equation where basically the infinitesimal generator of the Markov chain is expressed as a differential operator. And you see immediately there's something combinatorial going on because taking derivative dx of x to the n produces you precisely zero. So there's no way of doing that if there's no particle. And n times x to the n minus 1 models precisely the n ways in which you can do a removal. But I mean, you'll end up in a state with n minus 1 particles. So now you could think, okay, 400 slides later, you see how a Markov chain for graphs works. But it turns out it's much simpler than that with an algebra at hand. So we need a vector space, which I write in physics notation as ket, which now ranges over isoclasses of the states of the graph that you wish to have. And of course, making contact with the previous example, the only data you have of an isomorphism class of a finite set is the number of its elements, right? So far, so good. And then the real step is, so what replaces the differential operators? Well, you define, we had delta of R was the basis vector in this auxiliary vector space of a rule. Taking now a representation of the rule algebra means you assign a linear operator rho to each of these delta of R. And since it's linear, you only have to say what it does in basis elements. So rho of delta of R on X is defined as a sum over all the ways you can rewrite X using that rule R. And then, of course, by all the ways, I mean the outcomes, you again map it to the isoclasses. And again, You can, of course, get integer coefficients, which are the number of ways you can reach a certain output by rewrites automatically. No extra definition needed. Of course, under the hood, I described that this taking ISO classes, there's a non-triviality there, but let's say that's a moral concept at least. And now the real fun part starts to see that this row, if the underlying system is compositional, this row will be bona fide the representation of this rule algebra, of the associative unital algebra, on the vector space of graph states, of graph isoclasses. So it'll satisfy in particular this relationship if you apply in all possible ways one rule, and then to the outcomes in all possible ways a second rule. Alternatively, you can first look at how the rules could have interacted, and then just apply the composites, and you'll get the same distribution. Evidently, it's much simpler if your set X has 1 million vertices, and the rules are typically relatively small. It might be much more efficient to pre-compute the ways the rules can interact before attacking the state. And it gets better because we will, of course, do Markov chain theory in a moment. But just to complete the example, and this is really something, I don't know. For me, it'll turn out as a one-to-one mapping between these formal power series operators and rules. And it is what you expect, because x to the n was used as a basis vector to store the information of having n elements in the set. We will map this to the state of the finite set or finite graph with just vertices, which has n vertices. The multiplication operator with the formal variable will be the representation of the rule that inserts the vertex, and the derivative operator will be the representation of the rule that deletes the vertex. It has, because we're doing linear operators, I only have to show you that the coefficients on the basis chosen match, right? So this is here, because of course there's n ways to pick a vertex and then delete it from a set, right? From finite graph. And in the end of the day, using this rule algebra, on the right-hand side, you have the expression in the language of formal power series operators. And you see in particular, it's an x squared dx, right? It's not an elementary operation. But then using the representation property up top, I mean, I can just directly translate this as a dictionary shown here, and then use the representation property to get it in much nicer form, which is the one on the left. So the first part of the generator is just the representation of the rule that I chose. Nothing to remember. I take the representation of the writing rule that makes my jump. And the second bit is something interesting. It's an operator that takes the vertex, deletes it, and then adds another one. So does another round on a state, but with combinatorial coefficients by a number of ways it was possible to do so. And that will be a diagonal operator. And now if you know something about Markov chains, there will be a non-diagonal part which codes for the jumps, and a diagonal part which has to have the property that the row or column sum, depending on how you orient your vertices, has to be zero, right? It's this net flux zero requirement. And so a general Markov chain generator will you choose a set of rules, a set of basic rates. You simply can write down immediately the generator for a Markov chain. And that, in my opinion, and I would even argue that this representation of the autocatalysis reaction, I mean, it's a very clear insight. You take a vertex out, you put 2 in, that is exactly what's written here, right? And then we experimented with this a lot over the last 10 years in many different application scenarios. I mean, sort of the most out there is something we call rewriting theory for the life science, where we show how to do Markov chains for biochemistry or organic chemistry and how to really encode these molecules. We tried a little bit about social network models, but only, I mean, that was more of a technical case study to see if we can use a tool from industry for rewriting efficiently to reproduce some known details about discrete time Markov chains, such as the Volta model, which worked, but I mean, we didn't have the application. We really just wanted to see that this technique would be applicable in principle. So it would be interesting to discuss. And then there's combinatorics. And again, let me maybe just jump to the last. Can I have 5 minutes?
Sure.
Yeah, because I wanted to show you something, because Markov chains are a little bit tricky because you also have this continuous time aspect. So in a Markov chain, I mean, I claim that this formula I gave has all the definition of a semantics of a continuous Markov chain, because then you basically run this against, you have a differential equation system, and you can run it, and you can evaluate observables and so forth. It's a long story, but it is the full definition of a continuous Markov chain. It's still very counterintuitive, so I thought I would maybe close on a concrete example from combinatorics that just highlights this idea a little bit. It's a similar, here the point is, we take a data structure, planar rooted binary trees, and I only chose this example because there's a particularly simple way of sampling from a uniform distribution of all possible such things at a certain number of vertices. So if you think about it for a moment, if you want to have a planar rooted binary tree with, let's count correctly, I think 100 vertices, there's 200 factorial over 100 factorial possible ways of having such, up to, I mean, there's noise movement, but, and so a sampling algorithm that gives you uniformly chosen at random sample from, let's say, the distribution of all possible trees at size 100 is heinously difficult. So it's very surprising that there's an algorithm, linear generator algorithm, that can sample this with a linear cost, even though it's growing exponentially in the number of vertices. And the trick is, well, you do a rewriting system rather than a sampling, but a non-deterministic one. So in each step, you have a small grammar of vocabulary of steps you can do. You have to choose at random. And the step is very, very simple. I'm trying to visualize it here. In your current state, you pick an edge, be it the root, the left or right edge kind. You keep the endpoints of that edge, but remove the edge itself. And then you have two options of inserting this little Y-shaped thing. And what I'm trying to visualize is, so the bottom of this Y needs to be of the same kind as the original edge. Otherwise, of course, you might destroy your tree structure. And then there's a left and a right pointing thing. And either the left pointing is a new leaf or the right pointing. And these two options you choose at random. So you choose at random which edge and at random which of the two options. And this will produce you a uniform sample. And you can see, of course, the cost of sampling is, I shouldn't have said linear. Linear is maybe misleading. I meant in each step you have the number of edges in the tree, which is proportional to the number of vertices, times 2. But I mean, it's not exponential. That's what I was trying to say. Anyways, and now comes the really fun part. So this is now our generation procedure. And now one can ask, how does this? So I want to convey to you that the kind of arguments one can do here, you probably have seen in some other shape before heuristically. What I'm going to say is that each application will make two more edges, right? Something trivial. I can just count. But why can I count? That's his point. And here's where compositionality comes in. So I can look at how an edge came to be in the state after applying the transition. And if it just touches at one of the vertices there, well, I didn't do anything to it. It was there before. That's possible in both directions. Again, like the other point that I kept, whatever was there, I didn't touch it. So that's possible in both directions. But now, if I look at so I now have 3 other edges where I can attack. And now something interesting happens because these edges I didn't have before. So on the top, there's 3 candidates where I can match, right? Which I simply didn't have before. And conversely, on the bottom, I have 1 edge that I delete. So again, like I have the guys that are simply just null rounds, I kept them. But there's 1 edge which I delete. So that one I cannot see on the other order of events. I mean, first applying and then counting. And now the analysis that one performs is so-called commutator. Just as in quantum mechanics, I'm performing a commutator between a diagonal operator that counts edges. And I mean, the operator is just a matrix that on each basis state gives me back as coefficient the number of edges. I take the commutator of that operator with the operator that is a representation of this particular rule. It turns out the commutator doesn't see these things that are commutative. And it just gives me back the 3 options to get an edge. Overall, I'm just applying the generator though. I mean, it doesn't modify the shape of the generator. And 1 option before. And now I see indeed an equation that says the commutator of this, first count and then create minus first create and then count. gives exactly a coefficient of 2, which is the net win in number of edges. You can replay that game for higher tree patterns. You can compute these commutators. You get wild-looking equations, which causally can be explained through trace widths, but maybe that's another step. But what is the benefit? Now we can use that to give an evolution equation, because what I didn't say is basically there's a way of computing evolution equation on formal power series with this. Let's maybe just skip to the take-home message. And in the end of the day, what I can extract is a formal evolution system which will track the counts of 4 different kinds of patterns, which are shown here. So Y shapes, left come with 2 leaves, I guess, and left with 3 leaves, and also the number of edges. And each time I apply a generator, this will consistently change any given tree state with a certain quadruple of counts to another quadruple. And the interesting bit here is, it turns out that 2 of them are always linearly dependent on just the number of generations, how many times I applied the generator. But the other 2 have a very, very interesting joint probability distribution. And I'm showing here how if I iterate all the possible applications of the generator, because that's what this equation encodes, I'll get a probability distribution, a discrete support one, over the inhabitations of the possible combination of counts of having 2 versus having 3 leaves on these comb-shaped trees. So, and what I want to emphasize is, so at 100 steps, which is where this ends, the support in the space of the original data structure is of cardinality 200 factorial over 100 factorial. So 10 to the 217 possible states. This here is a joint probability distribution over 2 dimensions, which covers all the possible data you could measure on that system if you were to run any algorithmic experiments. And clearly, it's not. It's not even the shape of the support is, of course, not Euclidean. Also, the shape of the distribution itself is not. I mean, of course, it finally will approach law of large numbers at some point. But I mean, here I can show it to you at any intermediate state. And so, for me, one of the very important questions here is, if you have any system evolving over graphs and do that analysis on it, one possible analysis is to select a number of observations you do, like in quantum mechanics. Here, the observation is counting patterns and trying to reason about I marginalize the full distribution over all possible graph states, which I can never handle because it has too high dimension, by just giving the counts of certain patterns. If I choose this in an ill-defined way, it'll be meaningless because these equations have to close algebraically in a certain way. So it's not easy to construct such communicating sets, if you will. But if I do, then I have a system that is produced from my original system, and which has a property that for these properties that you track, you get the exact same distribution or evolution in a Markov chain. And so that seems to be a powerful tool, and we would be extremely interested, we as in the people I work with, to see if, for example, the analysis of networks by any hypergraph properties, if they can be described to local patterns, might exactly be an example of such type of analysis. And just to conclude, so, I mean, I've shown you some interesting perspective. This was for the rule algebra part of things. To say that it is still somewhat obscure, even though trace sets are needed to define this rule algebra, through these higher order, these decomposition spaces. It's not the case that I've ever seen any direct application of trace sets, let's say any approximation techniques or other, in practice. So there's a high chance of low-hanging fruit, so to speak, that when you're doing a network analysis and you're talking about something like the sequence of events that seems to be dominant to produce certain click shapes or so, that would probably be a tracelet statement. And also one of the other bottlenecks here is that while we now have a very good theoretical understanding, a very solid Markov chain theory, combinatorics, generating functions and such, and we have this little catalog for data structures and what could be compositional, we do not yet have proper implementation of these techniques. So that is a bottleneck. We might attack it soon. I mean, there's some group in Budapest I'm discussing with. But of course, as always, if there's any need from practitioners or any ideas, concrete data types we should try, that would be a very good discussion point, I think. And I suppose I'm well over my time, sorry.
Yeah,
so thanks a lot.
Thank you very much. Thank you very much.
Sure.
Wait.
Graph say molecule three or four coordination numbers were used for structural classes and classes. And it is a very successful application of it.
That sounds very interesting. Could you maybe send me a reference? Yeah, thank you. Yeah.
It's just stochastic matrices. All this moving is because there are energy barriers.
Right.
So you have to put Boltzmann factor. Not only the statistical, you have to just show you.
Yeah. So maybe we can even put the camera.
Glasses.
I mean, maybe it's 40 minutes.
One of the structural glasses is
Yeah, it was okay. We have things before.
Oh, okay, so not that.
We show excess concentration. So selenium, this kind of glasses usually they put hypermatrix.
Okay.
So it's three component. And you know what it is used for?
No.
Photocopying machine. It's called glass. It's like a sheet, which is photosensitive because of selenium. So the sheet is rolling like this. And this machine is so when you make a photograph, you put something and there's a flash of light, but before it goes to the chamber when you have make a photo, it is charged negatively.
Right.
So it's an isolator, so it keeps the charge. Now when the light goes on, selenium has this photosensitive effect, but the electrons are when I go up, but there is no light, electrons stay. The charge is
and then you
then you get something that is like a negative. Negative, which is the charge is where it's black, and there is no charge when it's white. Then it goes to another chamber, and black powder is put on, and where the black powder goes, where the charge is. So if there was no light, the powder will stick. If there was light, no. Then we go. There is another chamber when it's heated in order to make this powder go into the paper and you get so that's it. So this glass is elastic. It's fantastic. So this glass is made of selenium, which is two valence, and arsenic, which is three valence. So suppose the selenium goes with selenium. Tends to make spaghetti. So if you make a pure glass of selenium, it's like spaghetti. It's very brittle. But this makes it, first of all, it makes it more random. There's no
more branchings.
Branching. And also stabilizes. So now you have, so the idea was to check how it takes some energy to create this bond, another energy to create this bond. And yet another energy to create this bond. That's all. Yeah? So whenever you can have already something that's structured. right?
Mhm.
And so on. So you can always say this, there's a log and the rim. On the rim, you can have the following situations. One like this.
Because we have a talk.
Okay. Sorry.
Next person, because then we can discuss the sports.
Yeah, so
I mean, because as always, this is a hybrid, so
Yes.
I'm sorry.
Sorry. Yeah.
No, there is another person waiting. No.
So I want to. There's a couple of questions from the chat. So you can either read them or I can.
I can't see them right now, but
You can see them? Yeah.
no, I can't see them.
Oh, you can, and they're in the Zoom chat.
Yeah, but on this view, I don't see.
Oh, you don't see
Yeah.
them. Unrelated. So, first question is: can you think of dual vectors in the vector space representation of roots as patterns in your chase of data structure?
Just go with them.
Sorry.
What do you mean by, because that is an interesting question, exactly. You mean, what precisely do you mean by dual vectors?
Again, the dual vector space show.
I mean, what you can do is, because we are doing essentially stochastic mechanics, so I mean the version of quantum mechanics adapted to, not having Hilbert spaces, but L1 summable sequence, so on. What you can do is you can ask a linear operator that counts a pattern, and then have it followed by an operation that sums coefficient. I think that's probably the next to what you want to be a dual, because I mean, we can do Hilbert spaces, but then for the basis I showed, it would be really just pairing isomorphic graphs. That is probably not what you want. Although that could exactly count, of course, the exact graph coefficient, but I guess what you rather want is to count, I'm not sure, maybe you want exactly that. That would work.
Maybe the other question. The other question is, are you aware of any string diagram constructions, bracket pictorial manifestation of compositionality, with rewriting rules replacing linear maps and hypergraph patterns replacing types?
Yeah, I mean, basically, anybody coming from string diagram, especially from that X calculus, will know this work by Pavel Suboshinsky and collaborates Fabio Zanassi, Fabio Gaducci. Sorry, I'm forgetting somebody. There was a bunch of people who wrote three issues of string diagram rewrite theory. So anything you can do with string diagrams can actually be phrased in a certain kind of rewriting theory, and it's exactly on a certain hypergraph category. It's a little bit technically intricate because the way to get it to compose the way you want, you should read it. I mean, there's something about to plug two string diagrams together, there are some constraints you have to respect, but effectively string diagram rewriting or manipulation is exactly compositional rewriting theory. Yeah.
And one final question for myself. I was just curious, when you say you have one of these rule algebras, so say it's some unital associative algebra, how much can you use the classification theory of associative algebras to speak about the causal properties of?
I've frankly never quite thought about that, because I guess usually you wouldn't consider algebras. Are you talking about finite associative unital algebra? I mean, with finitely many generators?
Yes, or any.
Because these here would typically be infinite dimensional. So, I mean, I'm
infinite dimensional.
Because the generators of the algebras are finite, but you start out from a finite set of rules typically, but then you start composing them. And so in the full algebra, you have any possible. You can look at just the algebra generated by individual rules, but then this Lie bracket you construct, for example, might not close. So the set of generators. There are some sub-algebras that are finite, where really you just pick a number of rules, take their commutators under this the Lie bracket under this particular product, and you find that it is a closed algebra. But this is not the general situation. In general, it's countably infinite dimensional.
Okay, so the question is a bit more general in the sense that because if I see something like an associative algebra, some strong algebraic structure, like a half algebra or something like that, my question is more generally, do you have an intuition of how much you can use algebraic theory of these objects to somehow get insight on the causal properties of some rewrite systems?
Yeah, this is an interesting.
The data structures themselves, right? That's what you mean by causal structure.
Yeah, so
the causal structure of the rewrite.
Yeah, I mean, so the weird effect was, so in the beginning, we looked at, for example, just the Heisenberg-Weil case, where you have the generation of a vertex, the deletion of a vertex, and then in the Hopf algebra, the only non-trivial diagram can have is creating a vertex and then afterwards deleting it. That's the only non-primitive element, right? And then any sequence of events where you can just create and delete vertices will look at a decomposition of parallel creations, parallel deletions. So in the beginning, when we just looked at that, we thought, yeah, okay. So then you look at techniques used in Hopf algebras and basically look at the primitive and the ideals and whatnot. But here, I mean, the interesting bit was that, like I showed in this example with the trees, the commutators here are performing. They give some algebraic coefficients. It doesn't give any insight whatsoever. I mean, by the looks of it, it's quite unclear how on earth these wild. There are rules that basically take a large graph and just manipulate it in its slide position. That didn't seem to shed any light. Once you, however, remember that it all came from these interactions that are stacked together, you can actually visualize where these individual pieces come from and give a causal explanation. So my feeling is that it's really these tracelets that can give you explanations that you couldn't have seen in just algebraic theory, simply because the origin of these particular coefficients and algebra, I mean, the structural coefficients of the algebra are from causality of sequences of rewrites.
Sure.
And so that is, but I'm not saying even after 10 years that we have any, I mean, we have a few selection of examples which, if these commutators are really close at first level, just the lead bracket is really close, you usually have everything you could imagine intuitively explained. If they're close at a second order, if you have to take nested lead brackets to get any sort of algebraic closure, intuitively it's clear you need to speak about two-step sequences that can give rise to the contributions. And in fact, I think for Richard's model, I wouldn't be entirely surprised if one looks sharply at it and sees that